Good morning. Today I'm going to produce two very short videos on the topics from section 5.2. I just want to reinforce the idea that even though you may watch these videos and you may get something out of them, there's not a lot to them in terms of many examples. So if you need more examples or you want to see solutions of problems you've tried, please send me an email. I'll produce a video, or I can even probably talk to you through email and walk you through some things. Also, make sure you do read the sections. I try to point out a few things that are important, but if you scan the sections and read them and study the examples the best you can, that will also help. One of the topics, well, first of all, we're going to seemingly move into something that seems rather unrelated from what the section 5.1 problem set was about. Of course, that was all about anti-differentiation or integration, kind of reversing the process of differentiation. Its uses could be to solve differential equations, to just evaluate an integral, and even to solve some physics problems and motion problems, working from acceleration to velocity to position. So here we're going to build the foundation for a geometric understanding of what integration is. You may remember with differentiation, we started with the geometry. The derivative was considered to be the slope of a tangent to a curve at a point, and then it just ballooned from there. Here we looked at the process of finding the antiderivative or integral without really knowing what that means graphically. And over the next week, we'll start to build that understanding because it does take a while. In order to do that, we need to be comfortable with some notation known as sigma notation. You've seen this in other courses, so hopefully most of this is going to be a review. First of all, sigma notation is named because of the Greek letter sigma. Now, the sigma notation really has three components to it. One, you want to have something here, you want to have something above it, and you want to have something in that position. Okay, an example might be is that this is going to be a function, or the rule. This is kind of where things start. And this is kind of where it ends. One may look something like this. We have the sigma of I squared. Now this function could be in terms of x, it could be in terms of n, it could be in terms of any variable. We sometimes use I because we can consider this to be an index. So this sigma notation means sum. So rather than sigma notation, many people refer to it as summation notation. Nice little ring to it. And all this means is we are just going to put numbers from 1 through 5 in for I, and then add them all together. So it's just going to be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. We add these together. Get 1 plus 4 plus 9 plus 16 plus 25. And then we're going to get 20, 45, 10. What is that going to be? 20, 55. 4, 9, 16, 25. Okay. And so that's basically what we would call evaluating something using sigma notation. Now, if for some reason I only went from 3 to 5, it's not that we're doing 5 different numbers. We would only use 3, 4, and 5. So this is where you start, that's where you end. It doesn't indicate how many you might use. Now, with this sigma notation, we end up having what we could call many, rules and versions that will help us simplify things. So let me list some of these. These are some formulas for sigma notation, basically properties. What if I have I going from 1 to n, n could be any number I choose, and it's a constant, c? Well, you're basically adding c plus c plus c plus c plus c plus c n times, and that's going to be a repeated addition, which we know can be written as multiplication, so c times n. Here's another one. What if we add the numbers from 1 to n of the function I? Well, what this would look like, off to the side maybe, it would just be 1 plus 2 plus 3 plus 4 plus 5 plus ... And from a previous course that you've studied, this is an arithmetic series. And it's basically the sum of an arithmetic series. Well, in this case, the sum of this arithmetic series is n times n plus 1 over 2. It's basically the first term, the last term, and half the sum of half the number of terms. So you can review that on your own if you need. Now there are others for I squared and I cubed, and those are listed on page 295. Now you're never going to be required to know those from memory. So what that means is if you just refer to these formulas on page 295, if you run into a problem, you can just copy them and use them. And I want to make use of one of those to illustrate another example. Let's say we want to find the sum as I goes from 1 to n of I plus 1 over n squared. And I want to use for n equals 10. Well, if I were to do this, this would be from 1 to 10. That would be 10 squared, or 100. So I'd have to put a 1 in, a 2, a 3, a 4, and a 5 in for these I values all the way up to 10. So it looks something like this. It would be 1 plus 1 over 10 squared plus 2 plus 1 over 10 squared plus 3 plus 1 over 10 squared. Again, I'm just letting I go from 1 to whatever the number 10 is. And this is going to keep going to where it's 10 plus 1 over 10 squared. Well, if we were to add all of these together, we would get that sum. Well, what if this were 100? All of a sudden, I don't want to do this calculation. So what I can do is create a new formula in order to do it all in one big calculation. And that's what this example is about. So what I can do is this. Get another color. I'm going to rewrite this in a little bit different form. First of all, this n squared is a constant. There's some properties. I can rewrite it as 1 over n squared times the sum of I plus 1 as I goes from 1 to n. We also have properties of summation that you can study in the text that will allow us to write the sum of I plus the sum of 1. Both of those going from 1 to n. So each of these then could be simplified based on these formulas. So this would become 1 over n squared times the sum of I from 1 to n is all of this, n times n plus 1 over 2. The sum of 1 from 1 to n is just going to be c times n, so 1 times n, which is n. Now, I've taken the liberty to do this calculation, and if you would perform all the algebra involved here, we'd have n plus 3 over 2n. So now, if I wanted to find this summation for when n is 100, all I'd have to do is put 100 where the n is. So instead of performing every single one of these calculations, I can use this formula to evaluate the sum. Now, this is nice. It's not going to be fundamental to everything we do in this course, but again, I'm trying to lay the foundation for things that we may do in the future so you're comfortable with this notation. It does turn out that these can be done on your calculator, all of these summations, so I'll leave it up to you to play with these. One more type of an example of something you could see in the text would be kind of the opposite. What I mean by that, what if we wanted to take a series, a bunch of things added together, and we wanted to...
Sorry, I didn't quite catch that. Could you please repeat it?
I said series, and so series just...
I'm not sure I'm hearing you correctly. My apologies.
Should not have the phone with me while I'm doing this. So, a little distraction there, but here we go. Let's finish this up. Let's say I were given this bunch of numbers added together, so I don't say the wrong word, and I wanted to write it in sigma notation. Well, one of the keys is to realize that some of the things are changing and some are not. As we look through every single one of these terms, we want to focus on what is not changing. The 6 is always there, so that's going to be part of my summation formula. This 2 is always there, so that's going to be part of the formula. What changes is this position, this number. And we can see, because of this dot, 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 it goes from 1 to 11. So that's what I'm going to use for I, and then I'll just let I equal 1 to 11. So, in closing, part 1 of section 5.2, you will see in your problem set several problems that will ask you to evaluate summation. You can either expand them all, which in many cases is fine, and add them together. That's all it means. If it gets to the point that we're trying to find so many of them added together that we don't want to do that, we may use these formulas to try to transform one sigma notation into a much simpler formula, and then just put the number in that's required. And then there will be some problems that you will be given a bunch of numbers added together, expressions, and then you're trying to condense that into one expression using sigma notation. That's all for part 1. I'll work on part 2 shortly, and have a good day.